Hello बच्चों, welcome to our channel Point Basics. This is our fifth video or session in this series for JEE mains previous year questions for chapter wave optics. Before this video, we have made 4 videos in this series and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing for those, then you can watch those videos with them, or you can get some additional practice also. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, you can scan any of these QR codes in front of your screen. With this, let's start today's video. In the previous one, we covered up to around 40 something. This is covered. Okay, we will start with 48. So here, a beam of a plane polarized light of large cross-sectional area of uniform intensity 3.3 watt per meter square falls normally on a polarizer. Cross-section area is given, which rotates about its axis with angular speed is given. The energy of the light passing through the polarizer per revolution is close to. So we have to find out energy of the polarizer. Now we know that according to law of Moore's, we have I is equal to I naught times cos square phi. Now we know that intensity is basically power by area. So power is intensity times area. So if we multiply both sides by area, we will get IA is equal to I naught times A into cos square of phi. So this relation turns into that P is equal to P naught cos square of phi. Now we have to find out light passing through the polarizer per revolution. So as we need to calculate energy here, we know that energy is basically, or not energy, we can say power is basically energy per unit time. So if we are able to calculate the power, then we can easily equate it to E energy by T. So and T here will be time for the here per revolution. So time for the one revolution, and here we have omega. Omega is 31.4. So that will be equal to 2 pi by T. So time period, that will be 31.4 divided by 2 into 3.14. That will be 10, and this will give us 5. So T will be equal to 5 here. So we need to calculate their power. Now as we have to calculate power for the whole rotation, for the whole single rotation, what we can do, we can take average value. So average value of power will be P naught, because P naught is constant, so its average value will be equal to its original value, that is P naught, into average value of cos square phi. Now average value of cos square phi is half, and value of P naught is, that will be, here we have, that will be intensity times area. Intensity is 3.3 into area, that is 3 into 10 raised to the power minus 4 divided by multiply by the half, that is cos square phi. Now this will give us 4.95 into 10 raised to the power minus 4, and this is the power. Now for power we can calculate the energy. So energy will be here energy will be power into time period, and that will be 4.95 into 10 raised to the power minus 4. I think we made a mistake in the time period calculations here. Let me rectify them. That omega is 31.4, that is 2 pi by T. So time will be 2 pi divided by 31.4. So that will give us 1 by 5. So now substitute value of T here, that is 1 by 5. So approximately what we will get 10 raised to the power minus 4, and that is option B. So option B will be the right answer. Moving ahead, orange light of wavelength is given, illuminates a single slit, of which single slit is there means there is diffraction. The maximum possible number of diffraction minima produced on the both side of the central maxima we have to find out. Now, in diffraction, we know that condition is reversed. For diffraction, we have A sine theta. This is the path difference that is equal to n lambda for the minima. Now, from this sine theta comes out to be n lambda by A. Now, sine theta has a limit that it cannot, sine theta has to stay between -1 to +1. So, this term which is equal to sine theta will follow the same limit. So, -1 n lambda by A will be greater than equal to -1 and will be less than equal to 1. And from this we can say that n lies between here A by lambda minus A by lambda to plus A by lambda. Now we have to calculate here A by lambda we have to calculate. Now A is the slit width, that is 6 into 10 raised to power -5 divided by lambda, that is 6000 into 10 raised to power -10. So this will be 1000, 10 raised to power -7. So 10 raised to power -5 into 10 raised to power 7, that is basically 100. Now we know कि जो center होता है, at center there is only maxima, there is no minima at the center. So actually what we will get only 99 minima on one side and 99 minima on the other side. So total this will give us 198 minimas. So total number of minima will be 198 here. Moving to next one. The aperture diameter of a telescope is 5 meter. The separation between the moon and earth is given with the light traveling wavelength. The minimum separation between the object on the surface of moon so that they are just resolved close to. So here we know that for resolving, theta is equal to 1.22 lambda divided by A, and this will be equal to suppose here this is the first object on the moon, this is the second object, and this distance x is the minimum distance between them which can be separable or which can be resolvable, and here we will get theta, and this distance will be radius or distance from the moon to the earth, let's say capital D. So from this theta will be x by capital D, and from this we can write that 1.22 times lambda, lambda is here 550 10 raised to power -10 divided by A, that is slit width basically, or for a means for a telescope this will be diameter, so that will be 5, and it will be equal to x by the distance between the earth and the moon, that is 4 into 10 raised to power 5 kilometer. So 4 into 10 raised to power 5 into 10 raised to power 3, converting it into meters, and when we solve from this we will get x is equal to approximately 53.68 meter. That is comparable to the option A, that is 60 meter. Let's move to the next one. A polarizer analyzer set is adjusted such that the intensity of light coming out of the polarizer is just 10% of the original intensity. Assuming the polarizer analyzer does not absorb any light, the angle by which the analyzer need to be rotated further to reduce the output intensity to 0. So suppose this is our polarizer and this is our analyzer at some angle. Now they are adjusted such that light coming out of the analyzer is 10% of the original intensity. So suppose we have I node here, then we have suppose IP here, and that light coming out finally here, that is I node by 10. So now assuming that the polarizer analyzer does not absorb any radiation, angle by which analyzer need to be rotated further. So we know that assuming that if this I node is a unpolarized light, so if this I node is unpolarized light, then IP will be basically I node by, and we will assume that this is unpolarized light, else we have to find out the angle of P with respect to unpolarized light, so that will add additional calculation. So that's why we assume that I node is the unpolarized light. Now suppose initially the angle between P and A is theta. So what happens that then I node by 10 will be equal to IP of cos square times theta, and this will give us I node by 10 in is equal to I node by 2 into cos square theta. I node get cancelled, and from this we will get cos theta is equal to 1 by root 5. Now what happens that we want to reduce the intensity to 0. So if we want to reduce the intensity to 0, suppose finally intensity is 0, so this is P, this is I node light, and after traveling through P, that is becomes IP, which is again IP node, I node by 2, and now this angle between P and A becomes phi. Now for light to be reduced to 0, this formula will give us 0. So 0 is equal to IP times cos square phi, and from this we can write that phi is going to be 90 degrees. So if we find out the value of theta here from this relation, then difference of theta and phi is the angle which we have to rotate. Now from this, if we take value of theta, then theta will be cos inverse 1 by root 5, and that will be that theta is 63.43 degree. So the rotation which we need, that will be let's say delta phi, that will be 90 minus 63.43, and this will be equal to 26.56 degree. Now the most nearest match is here option B. So option B will be the right answer. Now let's move ahead. The value of a numerical aperture of the objective lens of a microscope is 1.25. If the light of wavelength 5000 angstrom is used, the minimum separation between the 2 points to be seen as distinct will be. So now resolving power of a microscope is 2 mu sine theta by lambda, and that can be written as 2 times numerical aperture divided by lambda. So that will be numerical aperture is 1.25 divided by 5000 into 10 raised to power minus 10, and this will give us 10 raised to power 7 divided by 2. Now minimum separation is equal to 1 by resolving power, so it will be 1 by 10 raised to power 7 divided by 2, and that will be 0.2 into 10 raised to power minus 6, or we can say 0.2 micrometer, and that is nearest to the option A here. Now next one, a system of three polarizers P1, P2, P3 is set up such that the path of axis P3 is crossed with respect to the P1. So we can say P1 and P3 are inclined at angle 90 degree with each other. So suppose this is P1 and then this will be P3. Now P2 is inclined 60 degree with respect to P3. So suppose this is P2, then this angle is 60 degree. Then with respect to P1, its angle will be basically 30 degree. Now unpolarized light of intensity I node is incident on the P1. So here we have I node. So we know that if we have an unpolarized light, then after passing through P1, it will become I node by 2. After passing through P2, the angle between P1 and P2 is 30 degree. So this will become I node by 2 cos square of 30. Now after passing through P3, it will become, because angle between P2 and P3 is 60 degrees. So after passing through P2, P3, it will be cos square 30 into cos square of 60. Now we can solve this. So this will be I naught by 2. Cos square of 30 will be 3 by 4 and cos square of 60, that will be 1 by 4. So this will be 3 I naught times 632. Now we have to find out intensity ratio of I naught by I, and this is basically I. So I naught by I will be equal to 32 by 3, and that will be 10.67. That is option C. Next one. So here we have a diameter of objective lens of telescope is 250 centimeter. For light of wavelength 600 nanometer coming at a distant object, limit of resolution of the telescope is nearest to. So limit of resolution means we have to basically find out theta here, and that theta will be equal to 1.22 times lambda by the diameter, and that diameter is of the objective lens, means the lens which is actually facing the object. So 1.22 times 600 into 10 raised to power minus 9 by t, that is we have 250 centimeter or 2.5 there. So from this we will get 2.92 into 10 raised to power minus 7, and this is theta, it will be in radian. So nearest will be option C for us. In the next one, limit of resolution for a telescope objective lens, diameter 200 centimeter, and it has a light to detect 500 nanometer coming from star. So again, theta we have to calculate, and that will be 1.22 lambda divided by the capital D. So 1.2 lambda, that is 500 into 10 raised to power minus 9 by t, that is 2, and on solving we will get 305 into 10 raised to power minus 9, that is option A. Now next one, in a double slit experiment, green light of 5303 angstrom falls on a double slit having separation of 19.44 micrometer, width of 4.05 micrometer. The number of bright fringes between the first and second diffraction minima is. So we know that width of the first maxima in diffraction is 2 lambda d by a, and for the second maxima this width reduces to half, that becomes lambda d by a. Now in case of interference, beta is lambda d by small d, where d is the slit separation. So the number of interference maxima inside the second maxima of diffraction will be, you can say, let's say that number is n, so that will be lambda d by small a divided by lambda d by small d. So lambda d get cancelled and we will get d by a, and that d is 19.44 10 raised to power minus 6, and a is 4.05 into 10 raised to power minus 6. So that will be approximately 5. We will get ratio as 4.8, and that is approximately 5. So option B will be the right answer. Now let us move ahead. So here we have a tank made of glass of refractive index 1.5 with a thick bottom. It is filled with a liquid of refractive index mu. A student finds that irrespective of what is the incident angle I, see figure, for the beam of light entering the liquid, the light reflected from the liquid's glass interference is never completely polarized. For this to happen, the minimum value of mu is. Now, as per the mention that it is, as per the question that it is mentioned that light reflected from this interference is never completely polarized. So means if light is never completely polarized, means it never, incident light never makes Brewster angle with the normal, and we know that Brewster angle or tangent of IP is equal to relative mu, and that will be equal to mu of the medium by mu of the environment or the nearby environment here. So here when light is striking at this point, then glass will act as medium, and this liquid, let's say water or some liquid, it will act as environment. So here we can say that tangent of IP for this one will be equal to 1.5 divided by mu. Now if we apply here, let's say law of Snell's law, then here this angle will be R, and due to parallel lines this angle will also be R. So basically tangent of IP, that angle IP is equal to going to be R. So let me zoom it out and slide it so that we can start. So here we can write using this one that tangent of R is equal to 1.5 by mu. Now this can be written as sine of R by cos of R is equal to 1.5 by mu, and this can be written as further sine of R divided by under root 1 minus sine square of R is equal to 1.5 by mu. Now applying Snell's law at this point, we can write that 1 times sine of I, because here we have air, this is liquid of refractive index mu, and this is glass of refractive index 1.5. So if we apply Snell's law at this point, then 1 into sine of I will be equal to mu times sine of R. So from this, sine of R is equal to sine of I divided by mu. Now we can substitute this value here, because it is mentioned that for every value of whatever value of I. So what we will do, we will make this expression in terms of, we will reduce this expression in terms of sine of I. So this will be sine of I by mu, and under root 1 minus sine square I by mu square is equal to 1.5 by mu. Now this will be further can be written as, here mu after under root will get cancelled, so this will be sine of I under root mu square minus sine square I is equal to 1.5 by mu. And if we square both of these sides, what we will get sine square of I divided by mu square minus sine square of I is equal to 1.5 square divided by mu square. Cross multiplying, and we will get mu square sine square I is equal to, this will be 3 by 2, and square of 3 by 2, that will be 9 by 4. So that will be 9 by 4 of mu square minus sine square I, and from that we will get 4 mu square sine square I is equal to 9 mu square minus 9 of sine square I, and from this we can find value of mu, and mu will be 3 of sine I divided by under root 9 minus 4 of sine square. Now what we have to do, we have to find out maximum value of mu. So for that, let us take that I is equal to 90 degree. because it does value of I does not matter as per the statement. So for I is equal to 90 degree, this mu will come out to be 3 by root 5. If we take I is equal to 0, then mu will be 0, and we have to find out maximum value. And let us take some intermediate value, that if I is 30 degree, then this will be mu is equal to 3 sine 30 is going to be half. So that will be 9 minus 1 by 4 into 1 by 4. Sine 30 is half. So this will be 3 by 2. And here we will get 9 minus 1, that is 8. So under root 8. And that can be written as 3 by under root 32. So we can see that denominator is increasing as we are increasing the value of angle I, means maximum possible value is 3 by root 5. So here it is. That matches with option B. So option B is going to be the right answer here. Now let us move to the next one. The angular width of the center maxima in a single slit diffraction pattern is 60 degree, and this is for diffraction. The slit width is the width of the slit is 1 micrometer. The slit is illuminated by monochromatic plane waves. If another slit of same width is made near to it, Young's fringe can be observed on the screen placed at a distance 50 centimeter from the slits. It is observed that fringe width is 1 centimeter. What is the slit separation distance? It means the distance between the centers of each slits. So here, now in case of diffraction, width of central maxima is given by, that is 2 lambda capital D by small d, and angular width will be omega by d, that is equal to 2 lambda by a, and here angular width is equal to 60 degree, or we can say that is pi by 3 radian. So from this, lambda comes out to be pi times a divided by 6. Now this will be 3.14 into a, that is 1 micrometer, divided by 6. From this, lambda comes out to be 5.2 into 10 raised to power minus 7 meter. Now we have interference fringe width, and that is basically beta, and that is lambda capital D by small d. Okay, yeah, here it should be A, because in case of diffraction we normally write it as A, and for the interference we write it as D. So we got the lambda. We have the interference fringe width. Yes, that is 1 centimeter. So 1 into 10 raised to power minus 2 is equal to 5.2 into 10 raised to power minus 7 into the screen distance, that is 0.5 here, 0.5 meter, and divided by small d. So small d will be 5.2 10 raised to power minus 7 into 0.5 divided by 10 raised to power minus 2. On solving this, we will get 26 into 10 raised to power minus 6 meter, that is 26 micrometer, and that is option nearest to the option A. So with this, we end this video here. Hopefully whatever we have covered is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you like this video, then do press the like button, share it, and subscribe to our channel. Also, if you like to support us, then scan these QR codes. With this, again, thanks for watching, and we will meet in next video.